What on earth is a Hilbert space? It's one of those ideas that sits at the very heart of modern physics and math, but it's so abstract, so out there, that even the guy it's named after supposedly had to ask what it was. So let's jump in and figure this thing out.
And hey, if you're a little fuzzy on the details, you're in some seriously good company. The story goes that the legendary mathematician David Hilbert, yep, the man who laid all the groundwork for this stuff, was sitting in a lecture given by his colleague. And at the very end, he apparently put his hand up and asked, "Excuse me, what is a Hilbert space?"
Now, that story is almost certainly just a legend, a bit of mathematical folklore. But you know what? It perfectly captures just how deep and powerful this idea really is. So that's what we're going to do today. We're going to answer Hilbert's question by building the whole thing from the ground up, starting with some simple geometry that we all know and love.
That's right, we're not starting in some weird abstract dimension. We're starting right here with stuff you've definitely seen before. Because a Hilbert space, for all its scary-sounding name, is really just a souped-up, super powerful version of the geometry you learned back in high school. And it all kicks off with one simple picture.
Remember these guys? A simple arrow on a graph. You just define it by how far you go sideways on the x-axis and how far you go up on the y-axis. This little arrow, this humble 2D vector, this is going to be our anchor. It's the picture you need to hold in your head for this entire journey. And what's so cool about this is how beautifully it scales up. All the rules that work for a flat, 2D plane, they work just fine in 3D space, too. And from there, mathematicians thought, well, why stop there? You can generalize this to any finite number of dimensions, what we call n dimensions, even if we can't really picture what that looks like.
Okay, but to actually do anything in these spaces, we need a tool. And that tool is the dot product. You probably remember this. You take two vectors, you multiply their matching parts, the x's with the x's, the y's with the y's, and then you just add all that stuff up. Now, here's the part you got to remember. This is not just some random busywork calculation. The dot product is our geometric Swiss Army knife. It's our ruler, it's our protractor. It gives us a solid way to measure how long our vectors are and what the angle is between them. And this idea of measurement, it is absolutely crucial. All right, so we've got our tools for finite dimensions. Now, take a deep breath, because this is where we take the big leap. We're about to take everything we just talked about, vectors, dimensions, measurement, and launch it into an infinite number of dimensions. And this is where your brain has to stretch a little bit. In this crazy abstract world, a vector isn't just an arrow anymore. It can be pretty much any mathematical object that follows a couple of simple rules, like you have to be able to add them and stretch them. So an infinite list of numbers, that can be a vector. A big grid of numbers, a matrix, yep, that's a vector too. And here's the big one for physics. Even a function can be treated as a vector. Okay, so to turn our wild infinite dimensional space into a respectable Hilbert space, it needs to follow two very important rules. And the first rule is this: the space has to be complete, which is just a fancy way of saying it can't have any holes or gaps in it. To get what that means, think about it like this. Imagine you've got a line of numbers, and they're all marching along, getting closer and closer and closer to some final destination. The big question is, does that destination point actually exist inside your space? For example, let's look at the rational numbers, all the fractions. You can cook up a sequence of fractions that gets infinitely close to the square root of 2. But the destination itself, the square root of 2, isn't a fraction. It's a gap in the number line. But the real numbers, well, they complete the line by filling in all those gaps. For every sequence that's heading somewhere, the destination is already there, waiting for it. So that's our first rule, plain and simple. A complete space is a space where every sequence that looks like it's converging on a point is guaranteed to land on a point that's actually in the space. No gaps, no missing points, it's all there. But hang on a second, that brings up a pretty big question. How do we even know if a sequence is getting closer to a destination? I mean, to talk about distance at all, we're going to need that ruler we mentioned earlier. And that brings us to our second rule. See, a basic abstract vector space, even a crazy infinite dimensional one, doesn't just automatically come with a way to measure lengths or angles. And if you can't measure distance, then this whole idea of completeness and getting closer is totally meaningless. The solution, the hero of the story, is something called an inner product. Just think of the inner product as the supercharged works-on-anything version of the dot product we saw before. It's a formal rule that we add to our space, a rule that lets us measure the length of any vector and the angle between any two, even if those vectors are functions.
And we've done it. We've gathered all the ingredients. We started with a simple arrow, we blasted it off into infinite dimensions, and then we added our two non-negotiable rules. So let's put it all together and finally answer Hilbert's legendary question.
First, you start with a vector space, just a big collection of things, arrows, lists of numbers, functions, whatever, that you can add together and scale up or down.
Then you bolt on an inner product. This is our universal ruler and protractor. It gives us the power to measure lengths and angles everywhere in the space.
And finally, you make one critical demand, that the space must be complete. No gaps, no missing points. Every journey has a destination inside the space.
And boom, there it is. That's the definition. A Hilbert space is a complete inner product space. It's an infinite dimensional playground where we can do geometry, but with all the mathematical rigor we need to make sure our calculations don't fall through any gaps.
So why does any of this matter? Well, this abstract playground is actually the backbone of some mind-blowing modern science. In signal processing, we use it to treat a complex sound wave as a vector and break it down into a sum of simple sine and cosine waves. And even more profoundly, in quantum mechanics, the very state of a particle, its wave function, is a vector that lives in a Hilbert space.
And that really leaves us with one final, incredible thought. This whole journey, from simple arrows on a page to these vast, infinite spaces of functions, shows just how powerful mathematical imagination can be. If the bizarre probabilistic reality of the quantum world finds its perfect language in a Hilbert space, what other deep truths about our universe are just waiting for us to dream up the right kind of space to describe them in?